So this machine is designed to aid in the recovery of patients suffering with radial head fractures. Now, a radial head fracture is a break in the radius bone in the arm, which is the top bone in the forearm, and the break happens at the top of that bone near the elbow. Now, the radial head is involved in flexion and extension of the arm, as well as rotation of the forearm. And when a fracture occurs, all this movement is limited, and so physiotherapy is employed to aid in the recovery of the elbow and help the mobility of the elbow. Physiotherapy is employed at different times depending on the severity of the fracture. If the break required surgery, then you would start this physiotherapy a week after the surgery. If it did not, it is important to start the physiotherapy as soon as possible. This machine is employed after this time, based on surgery or no surgery, to aid in the supination and the pronation of the elbow, and it will allow for a slow rotation of the wrist. You would generally use this at the start of physiotherapy when it is hard for the patient to do this on their own, and so they need aid of a machine to help them with this movement. This exercise will increase the range of motion for the arm by slowly strengthening the muscles surrounding the wrist. As the strength increases, the patient will be able to do this exercise without the support of this machine, and eventually, once the treatment has come to an end, they will be able to do it with dumbbells to aid in the support. So now I'm going to demonstrate the use of this product with the aid of a second person here. She is going to be my patient. So with the hand in, as you can see, as you move the mechanism, the wrist rotates.
The mechanism we just saw can be described as a crank rocker mechanism. This is a type of 4-bar mechanism. We will be looking at the kinematics of the crank rocker mechanism here. A free body diagram of this mechanism can be shown like this, with 4 vectors joined together in a closed loop system. It can be shown in more detail here in this diagram, where R1 here is the position vector of point A relative to point B, shown here as RB over A. The same applies for R2, R3 and R4. We are first looking at the position loop equation. In a closed loop system, it can be said that 4 vectors making up a loop can add together to equal 0. As shown here, the 4 vectors are RB over A, RC over B, RD over C and RA over D, all equal to 0. This is, we can split the vector RBA into its X and Y components here. So RB over A can be shown as R1 cos theta 1 in its X component and R1 sine theta 1 in its Y component here. For the position analysis of this crank rocker mechanism, we have these given values here. The given values are R2, which is 40 centimeters, R3, which is 25 centimeters, R4, which is 28 centimeters, theta 1, theta 3, and theta 4, with the values seen there. For the position analysis, we first need to create position equations. As you can see here, the sum of the X components are the R1 cos theta 1, R2 cos theta 2, R3 cos theta 3, and R4 cos theta 4. All of these components add up to equal 0. The same thing applies for the Y components of this vector, with R1 sine theta 1, R2 sine theta 3, R3 sine theta 3, R4 sine theta 4, all adding up to equal 0. In this equation here, we have subbed in the given values, where R1 and theta 2 are our unknown values. So we are given the equation R1 cos theta 9 cos 90 plus 40 cos theta 2 plus 25 cos 250 plus 28 cos 180 all equal to 0 again, and r1 sine 90 and plus 40 sine theta 2 plus 25 sine 250 plus 28 sine 180 all equal to 0 again. This equation here shows just a simplified version of this same equation, where cos 90 is equal to 0, which cancels out that part of the equation, and sine 90 is equal to 1, which leaves us with just r1. Over here, cos 180 is equal to minus 1, which leaves us with minus 28, and sine 180 is equal to 0, which leaves us with nothing here. To solve this equation, we are rearranging for theta 2. So as you can see, we have rearranged this first equation here to give theta 2, which is 23.97 degrees. To finish off this equation, we rearrange for r1 from this second equation here. Rearranging this, we give, and subbing in our value theta 2, we give 7.24 centimetres. This leaves us with our final position loop equation as, for the x component, 7.24 cos 90 plus 40 cos 23.97 plus 25 cos 250 plus 28 cos 180 equal to 0. And for the y component of this equation, we are given 7.24 sine 90 plus 40 sine 23.97 plus 25 sine 250 plus 28 sine 180 all equal to 0 again. From the position loop equation, we can perform velocity analysis using the position loop equation. We do this by differentiating this equation to form the x and the y components of the velocity equations, where theta 1, theta 2 and theta 3 vary over time. Known values here are theta 2 dot and theta 3 dot, where these values are the differential values of theta 1 and theta 2. Subbing in unknown values, including the angular velocity of theta 1, given as 10 revs per minute, we form this equation here. We then rearrange for theta 2 dot to give this equation here, equation number 3. We also rearrange equation 4 for theta 2 dot and then make them equal to each other here. We can rearrange this equation to make theta 3 dot the subject in order to give the final angular velocity of 2.65 revs per minute. The same applies with theta 2 dot. We sub the theta 3 dot value into the equation 4 here to give a final angular velocity of 0.62 revolutions per minute, leaving us with our final angular velocities of theta 1 dot is equal to 10 revs per minute, theta 2 dot is equal to 0.62 revs per minute, and theta 3 is equal to 2.65 revs per minute.